Awesome.
Right. Welcome, everyone. This is the seminar series for the School of Applied Mathematics, Getúlio Vargas Foundation. My name is Luis, and today we are very happy to have Rafael Tinaraj. He is a postdoc with the school under Professor Camacho, and he did his PhD at Orsay and also in RIA, I think. And he's going to talk to us about topological data analysis. So, Rafael, please.
Thank you, Luis. Thank you very much. I'm very happy, very glad to present this today. So the aim of this talk is to present to you topological data analysis, right? And more precisely, persistent homology. And I had to divide this in two talks. So today, I will define the basics of what is topology, algebraic topology. And next week, we will actually study persistent homology. And I'd like to start first with my favorite data set that should give you an idea of what's going on in this theory. So this is something from 12 years ago. So these authors studied the cyclooctane molecule. So this is a molecule that contains 24 atoms, right? 8 of carbon and 16 of hydrogen. And due to spatial constraints, right, due to the physical forces in game, several conformations, several configurations of molecules are allowed. And we'd like to understand how they behave, these conformations. So we can try to summarize one molecule by looking at its spatial coordinates, right? So each 24 atom in the space has 3 coordinates. So if I look at all the atoms, one molecule can be converted in a point in R to the 72. 24 atoms times 3 spatial coordinates. So here you can see one molecule that gives 1 point. And now the authors take a lot of these molecules. They generate a lot of molecules. And we end up with a point cloud, a set of points in R to the 72. And this point cloud happen to have some structure. And they show in this paper that this point cloud actually is close to something which is a sphere and a clay bottle. This point cloud draws a two-dimensional shape that is this union. And I think it is very interesting because we see here some emergence of topology, right? There is a geometrical object behind these data. And this should correspond to some physical law, something we can understand, right? And that's what they do then in the paper. So really, this should be the idea of topological data analysis. We have some data sets, and some of them may contain topology that should give us some insights, some ideas about what we are looking at. So this is topological data analysis. It is really at the intersection of at least 3 fields: algebraic topology, computational geometry, and data analysis. In particular, right now, machine learning. So wherever you are in this diagram, you have something in common with topological data analysis. And I hope I will show you in this talk what topological data analysis can do for you. And to convince you more of that, so this is the introduction of a book of Steve Udo, a very nice book about topological data analysis. And he lists at that time the several fields where topological data analysis has been applied. And you can see a lot of different fields, right? Image analysis, medicine, biology, chemistry. So it's really an exciting field. and people are still looking for subjects to apply the theory in. But before I explain you all of that, I have to introduce some basic notions. So we will start with topological spaces that are the main objects of topology. And then I will describe what is a topological invariant. So that will be a descriptor of our topological spaces that help to understand them. And then we'll be ready for the talk next week. Oh, by the way, please interrupt me if you have any question anytime. So we'll start with topological spaces. This is the very definition of topological space that I will remind, but if you've never seen that before, you can skip this part. So topological space, this is an abstraction of the notion of shape in math. It is a set, X, endowed with a collection of open sets. An open set is a subset of X, all right? This collection of open sets, we call that a topology. And a topology has to satisfy some axioms. So for instance, the empty set and the whole set have to be open sets. Infinite union of open sets has to be an open set. And also a finite intersection of open sets is an open set. And now we can define the notion of continuity between two topological spaces. So say I have X and Y, so two sets endowed with a collection of open sets. A map between them is continuous if when I take any open set of Y, its preimage by F is an open set of X, right? And so for those who never saw that, you can really think of that as so what we've done in first years of university with the epsilon delta calculus. Think about topological space as subsets of Rn, and think about continuous maps as maps continuous for the epsilon delta definition, right? All right, so let's have this idea in mind. So we can define a lot of topological spaces, a lot of subsets of Rn. For instance, we have the sphere, the cube, the open and closed balls, right? So I drew them here. But what happened is that the topology, all the set of topological spaces is very wide. And there exists a lot of topological spaces that do not admit a nice algebraic definition as these four ones, right? But in this large collection of topological spaces, some of them share important properties, right? So what we will do now is try to classify these topological spaces in sets that share properties. And these sets, these classes we will design, will be called homomorphism equivalence classes or homotopy equivalence classes. So we propose two ways of gathering topological spaces. Let's start with homomorphism equivalence. So I first define what is a homomorphism. Say I have two topological spaces, X and Y. A homomorphism between them is simply a map F that is bijective, continuous, and with inverse also continuous. If there exists such a homomorphism between two topological spaces, we say that they are homomorphic. So let me give you an example. The circle in R2 and the square are homomorphic, right? We can define a simple map between the circle and the square, who will be bijective continuous and inverse continuous. And so for a topologist, a circle and a square will be the same thing, all right? And the main interpretation of that, so basically being homomorphic means that we can obtain the first set as the other with continuous deformation, right? I can deform the square to obtain a circle. I give here an example of two spaces that are not homomorphic, the circle and an interval, a line. So it is not obvious to prove, but there is no way to define a homomorphism between the circle and the interval. They are different from a topological point of view. All right, so now we have the notion of homomorphic spaces. What we can do is gather topological spaces in two classes, where a class consists of all topological spaces that are homomorphic, right? So for instance, the square, it is homomorphic to a circle, but also to a triangle. You can easily define a homomorphism between them two. Also homomorphic to any polygon and any wonky circle, right? So this class for us will be simply the circles. The circle is not homomorphic to the interval, so we have another class, the class of intervals, right? Which is an infinite class. The class of crosses, etc. The class of spheres, I mean, there are infinitely many classes. And yeah, well, so I put these classes here. We still have to prove that they do not intersect. I mean, when I take an interval and a cross, I have to prove that the interval and the cross are not homomorphic, okay? And this is actually a complicated question. Given two spaces, are they in the same class? Are they homomorphic? In order to give an answer to this kind of questions, I will present in the next chapter the notion of invariant. And invariance will help us to solve this kind of questions. But for now, let me introduce another relation we can define on topological spaces, which is in some sense more suited to deal with what we'll do soon. And this is called homotopy equivalence. So first, I have to define what is a homotopy. And for that, I need two topological spaces, X and Y, and two maps, two continuous maps, F and G. So a homotopy between F and G will be, in some sense, a map connecting these two maps. Mathematically, a homotopy will be a map big F from X time 0, 1, the interval, into Y, such that, so if I fix the second parameter here to 0, I obtain a map with domain X, and I want that this map is equal to F. If I fix the second parameter to be 1, I want to obtain G. And moreover, I ask for this map to be continuous on this product. All right, if I have such a homotopy between two maps, I say that the two maps are homotopic. I give an example here on R. So let's consider F to be the constant map equal to 0, and G to be this kind of sinusoidal map. a homotopy between them two will be a continuous interpolation between f and g. And I choose one here, for instance, this continuous deformation, all right, that takes f to g. So f and g are homotopic. Now I can define homotopy at the level of topological spaces. Say I have two topological spaces, X and Y. So I will define a homotopy equivalence between them. A homotopy equivalence will be the data of two maps, one from X to Y and one from Y to X, such that the composition GF, so GF is a map from X to X, this map should be homotopic to the identity map on X. And conversely, FG, which is a map from Y to Y, must be homotopic to the identity map on Y. I have to be able to deform these maps to the identity maps. So this is a definition. If I can find such a homotopy equivalence between two topological spaces, then they are homotopy equivalent. And so homotopy equivalence is, in some sense, a weaker notion than homomorphism for the following reason. If I have two homomorphic topological spaces, then they are homotopy equivalent. So let me give you some intuitions about that. So with homotopy equivalence, we are allowed to deform continuously the spaces, right? As we did for homomorphism equivalence. But moreover, we are allowed to retract the space on itself, okay? For instance, this circle with a little hair here, I can retract this line. I have a circle. These two are homotopy equivalent. So this is an annulus, right? I can same retract the annulus on its inner circle. So the annulus and the circle are homotopy equivalent. The interval up, I can retract it on itself, on a point. So the point is equal to an interval from a homotopy equivalence perspective. And so if you follow me, you can understand that the letter A is homotopic equivalent to a triangle, which is also homotopic equivalent to a circle. So the letter A is a circle. All right. And we can do the same as before. We will gather topological spaces into classes, now according to the homotopy equivalence relation. And now we obtain way wider classes, because in the class of circles now, we will also have we'll have all spaces that retract on the circle, so even two-dimensional spaces. In the class of points, well, we find the interval, but also crosses. We find open and closed ball, etc. And we have the class of spheres, of tori, of Klein-Botters, right? So these are wider classes than with the homomorphic equivalence, but still contain each common topological objects. So let me give you an example of how that works. These are the 26 letters of the alphabet. And I want to classify them into homotopy equivalence classes. So what do I have? This letter A, we've seen that it is a circle. And we have other circles here. For instance, the letter D Well, it is homomorphic to a circle. It is so also homotopy equivalent. But the letter P, if we retract that interval, we obtain a circle. So we have a lot of circles here, but we have other classes too. For instance, the I, this is an interval, it retracts on a point. And the point is not a circle, homotopy-wise. So and there is a lot of other letters that are equivalent to a point here. And there is actually a third class, which is represented here. And this class is the class of the letter B. The letter B is homotopy equivalent to the bouquet of two circles, to the union of two circles, right? And the two other classes are the letters homotopy equivalent to circles and the letters homotopy equivalent to a point. I hope this is clear for everyone. Don't hesitate to interrupt. All right. So this is it for comparing topological spaces. Now, there are some questions. We classified topological spaces into classes, right? That should correspond to common topological objects. And we can ask first, well, if I give you a topological space, how do you determine in which class it belongs, right? So as you've seen with the letters here, for the letters, it's easy. Basically, you have to count the number of holes we have in our letters, right? So these are the letters with one hole. In some sense, we can see that the B has two holes and there is no hole in these other letters. But in general, it's hard to answer this question. And also another question. So what can we say about one class of topological spaces? And I write here, what are the common features of spaces in the same class? And I insist on the word feature because, I mean, this is a word we use in data analysis, right? When we want to describe an object, something, we use features. And you really can see what I will show you now, invariants as features, descriptors of our topological spaces. And oh yeah, I think it's an opportunity to cite Henri Poincaré here, who said, la mathématique est l'art de donner le même nom à des choses différentes. And this is exactly what we are doing here. So let's define some features, some invariants. And I will start with the number of connected components. So I have to define what is a connected space. Actually here, a path connected space. Take a topological space, take a subset of Rn here. I say that it is connected if for any pair of points you choose in your space, you can define a continuous map from 0, 1, the interval to x, such that f of 0 is x and f of 1 is y. So what does that mean? Given 2 points, I am able to define a continuous path that connects x and y. So in this second example, you see that x and y cannot be connected because there is nothing here. We cannot cross this area. Okay. And in general, for any topological space, we can define connected components. So we can subdivide, we can partition any topological space into connected components. Okay. that corresponds to subsets who are maximally connected. So for instance, this set here has 4 connecting components. And what is nice with this notion is the following proposition. If I have 2 spaces X and Y that are homotopy equivalent, then they have the same number of connected components. Okay. So in other words, the number of connected components is an invariant of homotopy class. It is a feature shared by all the spaces in the same class. And we can go back here. As you can see, if I take any class here, for instance, the class of circles, I have only spaces with 1 connected component. Actually, the 5 class I put here all have only 1 connected component. So I'd like to propose an application of that in theory and then in practice, in data analysis. So I wrote again the proposition. By the way, a consequence of that is if 2 spaces are homomorphic, then they also have the same number of connected components. Because if 2 spaces are homomorphic, then they are homotopy equivalent. And we can apply this proposition. So a very direct example. If I consider the interval 0, 1 as a first topological space, and the union of 0, 1 and 2, 3 as a second topological space, I can directly say that they are not homotopy equivalent. Because if they were, they will have the same number of connected components, which is not the case. We have 1 component here and 2 here. We can go a bit further. I can use this proposition to show you that the interval and the circle are not homomorphic. We can show that they are not homotopy equivalent, but this will be a little more difficult. So let's just prove that they are not homomorphic. By contradiction, I will suppose that they are. So we can consider a map from the interval to the circle, which is continuous, bijective, and inverse continuous. Okay. And now I will do something. I will remove a point from the interval. So pick x between 0 and 2 pi. Do not pick 0. It will not work. So remove x from this interval. My homomorphism from the interval to the circle will now become a homomorphism. It restricts to a homomorphism between the interval without the point and the circle without the point. I call this restriction map J. But the interval without a point is the union of 2 intervals. And the circle without a point is only 1 interval, right? So this object on the left has 2 connected components, and this one on the right has only 1. And this is absurd. We cannot have a homomorphism between objects with different connected components. So the first statement, the existence of a homomorphism between the interval and the circle, was impossible. Okay. I will show you now what does that mean in practice, connected component. Say we have a point cloud, a data set that is a point cloud in the plane here, for instance. So I say that finding connected components in data sets correspond to a classification task, right? Because, well, if you apply any algorithm to that, you will, I hope, obtain 2 clusters, right? As you can see. But you can see these 2 clusters as the connected components of some underlying space from which the points come from. I will try to reformulate that. You can see these data sets as a sample of this union of two ellipsoids, right? And at the end, trying to classify this data set, this point cloud, consists in finding for each point to which connected components it belongs. Okay. And yeah, so this is a general philosophy we use in topological data analysis. We will try to understand data sets as samples of some nice underlying shapes. All right. So this is it for connected components. The second invariant I want to present is called Euler characteristic. So let's start with the Platonic solids. So you may know this number. They are quite famous. The number of faces of edges and of vertices of each Platonic solid. This is a very nice sequence with nice symmetries. And there is a great relation between these numbers. And this has been proven by Euler. If you take the number of faces, you subtract the number of edges, and you add the number of vertices, you obtain 2. Okay? This number, I call it key. So this is true for any polyhedron, not only the regular ones that are shown here. So what it means that the combinatorial structure of this polyhedron have some nice relation. And I will now try to generalize this statement. And to do so, we will need the notion of simplicial complexes. So I hope I won't be too fast here, but basically what we need at the end in topological data analysis is to work with topological spaces on a computer. And we have to, in some sense, describe topological spaces in a way that computers will understand. And a nice way to do that is with the notion of simplicial complex. So a simplicial complex, I will read the definition. You start with a set of vertices, V. This is any set. A simplicial complex over V will be a collection K of subsets of V. These subsets, I will call them the simplices. One simplex, two simplices. And there is one axiom. For any simplex in K, its non-empty subsets, tau, must also be in K. Okay? I also define here the dimension of a simplex. It is its cardinal -1. And you can also define the dimension of a simplicial complex as the maximal dimension of its simplices. So let me give you an example. V is the set that contains 3 elements, and I consider this simplicial complex. All right? You can verify that it is indeed a simplicial complex. The subset of any of its simplices is a simplex. And so basically, what it means, simplices should be seen as pieces that we add to the complex. The simplices of dimension 0 should be seen as vertices, and the simplices of dimension 1 should be seen as edges, right? So I can draw my simplicial complex like that. And so this is a triangle. This is a circle. I can go into details here, but a simplicial complex is really a combinatorial object, a discrete object, though it corresponds to a continuous topological space. Okay, so in some sense, this discrete structure is a way to represent a circle, okay, a triangle. Another example, I take now 4 vertices, and I consider this simplicial complex. So now I have simplices of dimension 2, these faces here, right? And at the end, I obtain this object. So it is an empty tetrahedron. So this is a sphere. Okay, I can describe the sphere as this set, this simplicial complex. All right. Now I can define the Euler characteristic in great generality for any simplicial complex and not just polyhedrons. So let's take a simplicial complex K of dimension n. I define its Euler characteristic as the alternate sum of number of simplices of each dimension. So if you don't want to read this definition, you can just look at this example. The circle, the triangle, has 3 simplices of dimension 0 and 3 simplices of dimension 1. So I write chi is equal to 3 minus 3. This is 0. Okay. The Euler characteristic of the triangle is 0. If I do the same with my tetrahedron, I obtain 4 minus 6 plus 4. 4 being the number of 2-dimensional simplices, and this is 2. Okay. All right. And now, I guess you wait for the invariant property. And yes, the Euler characteristic is invariant. If I have 2 homotopy equivalent topological spaces, then they have the same Euler characteristic. By the way, if you look at this, so we show that the sphere has Euler characteristic equal to 2. And of course, this is the number we obtain for this polyhedron because each of these polyhedrons represents a sphere. They are all spheres. Okay. So as for connected components, we can use this information to prove that 2 topological spaces are not homotopy equivalent. For instance, the circle has Euler characteristic 0, the sphere Euler characteristic 2, so they are not homotopy equivalent. Another very important implication of that, the classification of surfaces. So you may know that surfaces, here connected and compact, and I should add orientable surfaces, are well understood. It's only a countable infinite family of surfaces. We have the sphere, the torus, the bitorus, the 3 torus, etc. And if you are given a sphere, connected, compact, and orientable, you can determine in which class it belongs by simply computing its Euler characteristic. So the Euler characteristic is enough to describe the homotopy classes of connected, orientable, compact surfaces. All right. And now, let me show you an application in practice. So thanks to the Euler characteristic, we get some information of about our space. And this is something people like to do in cosmology. So here is a picture of the cosmic web. So look at the universe. You have a lot of matter, right? Which has some structure. People say it has a filamentary structure, right? The galaxies. So actually, it's not obvious to describe the shape of the cosmic web because you can look at it at different scales. You can see it as an object of dimension 3. If you look at the holes, the cavities, the bubbles, the areas that form the galaxies. You can also see it as an object of dimension 2 if you look at the walls that the galaxies draw, and also as an object of dimension 1 if you look only at the strings, the filaments. But in each of these cases, computing the Euler characteristic will tell us something about the topology of this space, right? And so yeah, I put this other illustration in a paper of the same vein. So they use here the Euler characteristic. This is a cut of the universe. They use the Euler characteristic to count the number of holes there is in this structure, right? And in some sense, you can prove that in a graph, the Euler characteristics is linked to the number of holes of your graph. All right, I will talk a bit more about cosmology in the next talk next week. And all right, so let's go to the last invariant, Betti numbers. So the Betti numbers, this is not an invariant, but a sequence of invariants, a sequence of features. And it goes like that. To any topological space X, you can define a sequence of integers, beta 0, beta 1, beta 2, etc. And we call these integers the Betti numbers. Okay. And so it is not an easy task to define these Betti numbers. Unfortunately, I won't have the time today to give you the definition, but trust me, there is a nice way of defining these numbers. And yeah, so this is based on homology theory. But instead of building them, let me give you some examples. I consider 5 topological spaces here, and I wrote down their Betti numbers, the first 3 Betti numbers. Well, so this may be a bit mystical for some of you, but actually there are very nice interpretations of these numbers. So let me read that for you. First, beta 0, the first Betti number, is actually the number of connected components of your space. It's a theorem. You can prove that. So yeah, the point, the sphere, the circle, the sphere, two circles connected. All of these have one connected component. But at the end, these 2 disconnected circles, they have 2 connected components, right? We can read the number of connected components in the Betti numbers, the 0th one. Beta 1, this is the number of holes in X. So this is not a theorem. This is much more of an interpretation, right? But basically, what is a hole? A circle is a hole. A circle has a hole. 2 circles have 2 holes, all right? And also 2 disconnected circles have 2 holes. The sphere doesn't have a hole. It has a void, 2-dimensional hole in some sense, right? And as you can see, it is the only space here that has a non-zero beta 2. All right, so this is how we understand Betti numbers. Let me give you another important example, the Betti numbers of the torus. So it goes like that. Beta 0 is 1, because we have one connected component, right? Let's look at beta 2. Beta 2 is 1, because we have one inner void, right, inside the torus. And beta 1 is 2, because, well, you have, in some sense, two holes in the torus, all right? If you cut it in two perpendicular directions, you have two non-connected holes. Right. So these are the Betti numbers of the torus, 1, 2, 1. All right. So just as before, fortunately, the Betti numbers are, again, an invariant of homotopy class. If two spaces X and Y are homotopy equivalent, then they have the same sequence of Betti numbers, right? And again, we can use this information to discriminate between spaces. So let me give you here the Betti numbers of the sphere, the n-dimensional sphere, so seen as a subset of Rn plus 1, the unit sphere of Rn plus 1, has very simple Betti numbers. The ith Betti number will be 1 if and only if I is 0 or n. And it will be 0 else. Okay. So the top dimensional Betti number will be 1. And that shows that the spheres of different dimension cannot be homotopy equivalent, right? Which is something quite not easy to prove. I propose an application here, again in theory. So this is a very powerful notion, Betti numbers. We can prove a lot of things. Brouwer fixed point theorem, we can prove Borsuk-Ulam theorem. Here I propose Brouwer invariance of domain. So the theorem states that Rn and Rm, the Euclidean spaces, cannot be homomorphic if n is not m. Okay. It looks like the previous proof we did. By contradiction, I choose a homomorphism between Rn and Rm. Okay. And now, again, I will remove a point from Rn. Okay. So my homomorphism will restrict to a homomorphism between Rn minus a point and Rm minus a point. But you can prove that Rn minus a point is homotopy equivalent to a sphere, to its sphere. Basically, think about the plane, remove a point, then you can retract all the space and you obtain a circle at the end. And so this works in any dimension. On the left, I have a sphere of dimension n minus 1. And at the right, I have a sphere of dimension m minus 1. But as n and m are not equal, they cannot be homomorphic. And this is a contradiction, right? So we have proven Brouwer's invariance of domain. And now I'd like to propose an application in practice, how Betti numbers can be useful. So this is a very nice data set from a few years ago. So here they do image analysis. They collect a lot of natural images. So a natural image is simply an image you can have by taking a picture with your camera. We take a lot of natural images and they extract small patches, small sub-images, right, of size 3 by 3. images are in gray, so one patch can be converted into a 9-dimensional vector, right? So if we take a lot of patches, we obtain a lot of points in R9. And we can try to understand the topology of this point cloud. And it turns out, so what they do here is they try to compute the Betti numbers of this point cloud, of the underlying shape, and try to understand what it is. And they obtain the following Betti numbers. Beta 0 is 1, beta 1 is 2, beta 2 is 1, and beta 3 is 0. And now we could say, right, these are the Betti numbers of a space I know. So yeah, actually, you may think about the Betti numbers of the torus, but there exists another topological space that has the same Betti numbers, and this is the Klein bottle. And actually, they show that these points are close to a shape, which is a Klein bottle. They are able to embed a Klein bottle in R9 that will describe nicely the position of the points, right? And all of that started by looking at the Betti numbers of it and trying to deduce what could be the underlying topology. All right, so this is the end. So I show you how topology can emerge from data sets, how it can be interesting to understand it, to get how the data shape, the data sets behave, right? And in order to understand this topology, one can compute invariants that are nice features, descriptors of them, such as the number of connected components, the Euler characteristic, or the Betti numbers. And well, so there is still an important question here. How do we compute these invariants in practice? What does that mean? And this is actually the whole point of persistent homology, trying to compute robustly in practice these invariants. And this is it. Thank you, everyone, for listening to me.
Right. Oh, thank you for a wonderful talk. I have, so we're now open for questions. I have few, but I think you have teased that these questions I have about practicalities will be answered next week. So I'll take a step back, and if anyone wants to ask questions, now is the time. Please just open your mic and ask. And if you can't, just type them up in the chat, and I'll read them out. Thanks. Anyone? Or if you don't have questions, I'll ask mine. So the last proposition you showed, does that imply the other two? Because your talk is structured around these three very nice propositions. Does the Betti number proposition imply the other two? So you said that the first Betti number, right? So beta naught is the number of connected components, right? So am I right in saying that the last one then implies the, for instance, the first one?
Is there any relation between Betti numbers? Is that the question?
No, my question is, if you say that, so if you can go back to the slide where the proposition for the Betti numbers is.
Which one?
Oh, no, sorry. You just passed. Yeah. Yeah. So if you say that they are homotopy equivalent, they have the same Betti numbers, right? But if they have the same Betti numbers, then they have the same beta naughts. And if they have the same beta naughts, then they have the same number of connected components. So this implies the first one. Is that right?
Yeah.
Oh,
Yeah.
okay.
Actually, yeah, a number of connected components is already contained in the Betti numbers. I talked about connected components just for pedagogical purposes.
Yeah. I realized that at the end that, you know, and I liked it very much. You know, it's on
actually,
the story.
the Euler characteristic also is contained in the Betti numbers.
I imagine.
If you take the alternate sum of Betti numbers, you can prove that this is a Euler characteristic.
Oh, nice.
Yeah, it's a nice theorem. So actually, at the end, we only look at Betti numbers.
Yeah. Okay. Yeah, that makes sense. How easy or hard is it to prove? Because that's the first question I asked myself. For the first proposition I saw, I found it very interesting, but then I thought, how obvious is that? Is that obvious, Johan? Is this something easy to prove?
It's so easy to prove when you have the whole machinery of homology defined. Nice. But there is a lot of work, but at the end, all goes very smoothly, right? Even I like this proof of Brouwer theorem because it's such a hard theorem, but you can prove it in a few lines with this.
Yeah, it seems very powerful. Nice thought. Questions? Yeah. Actually, your talk made me rethink everything. You know, maybe I wasted my time in probability and statistics. I should have learned topology and, you know, persistent homology and whatever. This is so nice, you know.
But you can actually do a lot of statistics and probabilities with topology. As you will see next week. I mean, the problem of estimation of this invariance really is a statistical problem, right? And so we need statistics to talk about that seriously.
Questions? Maybe this is a sign that you did your job very well and nobody has any questions.
I hope.
Right.
Yeah. If you want to talk about that a bit more, you can, anyone here, you can contact me by email.
Yeah, I'll certainly contact you because one of the questions I have is a practical question, but I'm going to wait until next week to see if you're going to answer it. Yeah. But it has to do with when these objects, instead of being things that you can embed in Rn, are trees, you know, with loads of structure that can't be embedded. That you can prove that you can't embed that into Rn, and then how do you represent that in a computer? But I don't want to spoil anything, so I'll wait until next week.
Yeah, or this won't be a problem. Don't worry.
Well, Luis, I just wanted to say that the talk was really nice. Is the level we wish to have in this kind of seminar, and certainly the next talk will be more on the data science side. Okay.
Yeah. Okay. Yeah. Thank you very much.
Very good.
Right. So someone said that it's a very nice talk. So Soledad, I think, said it's a very nice talk. But there are no questions. So I'll stop recording now. We can stay here and chat.